What if the universe is made up of tiny fragments so small they can't be seen? And what if these fragments tell us that gravity, as we know it, is just the beginning? For centuries, gravity was a mystery that we thought we had solved. We thought it was a fundamental force, an invisible thread binding the cosmos together. But modern physics tells us something else, something stranger. Have you ever wondered why gravity can form entire galaxies, but remains invisible to us? Some modern scientists now believe that gravity may not be fundamental at all. Instead, it may be an emergent phenomenon, generated by the entanglement of particles and fluctuations of spacetime itself. If this is true, then everything we think we know about gravity could be wrong. New experiments are already being designed to prove this theory, and if they succeed, we'll be forced to rethink the rules of reality. Let's take a closer look at all of this. Gravity, at first glance, seems deceptively simple. It's the force that makes objects fall, anchors us to the earth, and controls the movement of celestial bodies. On closer examination, however, gravity turns out to be one of the most mysterious forces in the universe. Among the four fundamental forces, electromagnetic, strong nuclear, weak nuclear, and gravity stands apart. It is the weakest of the four forces, but paradoxically, it influences vast distances, holding galaxies together and shaping the universe itself. Gravity is unique in that it's purely attractive. The electromagnetic force, on the other hand, can both attract and repel, depending on the charges. Gravity, however, acts uniformly. It attracts everything, regardless of their nature, from dust particles to entire galaxies. This simple attraction creates a profound order, influencing the formation of everything from planets to the large-scale structure of the universe. At a basic level, we understand gravity through Newton's law of universal gravitation, which tells us that each mass exerts a gravitational pull on all other masses, proportional to their masses and inversely proportional to the square of the distance between them. But this insight, while useful, doesn't fully explain the underlying mechanisms. Why does gravity act in this particular way? How does it penetrate space, acting at distances where other forces fail? The next step in understanding came from Einstein's general theory of relativity. Instead of viewing gravity as a force that attracts objects to each other, Einstein proposed that gravity is the result of massive objects warping the very fabric of spacetime itself. In this model, objects such as stars and planets distort spacetime, creating its curvature. Smaller objects then follow the paths laid out by this curvature, like a metal ball rolling across the surface of a stretched canvas. This geometric understanding of gravity elegantly describes a wide range of phenomena, from the orbit of planets to the curvature of light around massive objects known as gravitational lensing. However, even this revolutionary model has its limitations. General relativity is not fully consistent with the quantum nature of other fundamental forces. And this leads us to the question, gravitation really a force, or is it something else entirely? One of the main mysteries is that gravity, unlike the other forces, does not fit into the standard model of particle physics. The other three fundamental forces have corresponding particles: photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. But the particle that carries the gravitational force, the hypothetical graviton, has never been observed. The inability to fit gravity into the quantum framework is one of the greatest mysteries in physics. The puzzle becomes even deeper when we consider the role of gravity on cosmological scales. It is gravity that dictates the motion of galaxies and the structure of the universe, pulling matter together in clusters and forming cosmic voids. At the same time, it is gravity that plays a critical role in the collapse of massive stars into black holes, regions where the gravitational pull becomes so strong that even light cannot escape. These extremes push the limits of our current understanding, hinting at the deeper mysteries yet to be uncovered. The need for a deeper theory that unites the macroscopic picture of relativity with the quantum realm remains pressing. Gravity is a force we live with every day, yet we fundamentally misunderstand it at its most extreme and smallest scales. It simultaneously governs the entire cosmos, and yet defies our understanding. The attempt to create a quantum theory of gravity is one of the most ambitious endeavors in modern physics. Quantum mechanics describes three of the four fundamental forces: electromagnetic, strong nuclear, and weak nuclear, through the interaction of their respective particles. However, gravity remains elusive within this framework. Unlike other forces, gravity does not obey the rules of quantum theory, which creates significant difficulties when scientists try to combine it with other forces in the standard model of particle physics. In the quantum realm, forces tend to manifest themselves through particles. The photon, for example, carries the electromagnetic force, and the gluon carries the strong nuclear force. However, theoretical physicists suggest that gravity must also have a force carrier, a particle known as the graviton. Gravitons, if they exist, must be massless, move at the speed of light, and have a spin of 2, a key characteristic that distinguishes them from other quantum particles. Imagine you're holding an ace playing card. If you rotate it 360, it will look the same again, much like a photon, a particle with spin 1. Now, take a face card, such as a queen. Rotating it halfway, by 180, is enough to make it look the same. This is how a particle with spin 2, such as the hypothetical graviton, behaves. And for particles like electrons, which have a spin of a half, things get even stranger. You have to rotate them twice, by as much as 720, before they look the same. This is just one of the oddities of the quantum world. The idea of gravitons has arisen from the desire to quantize gravitation in the same way as other forces. However, gravity is fundamentally different from other forces. While electromagnetic, strong, and weak forces dominate at the quantum scale, the influence of gravitation is much weaker in comparison. This weakness becomes an obstacle to the formulation of a quantum theory, since gravitational effects are difficult to detect at the subatomic level. Moreover, Einstein's general theory of relativity, which explains gravity as a curvature of spacetime, works extremely well on large scales, describing planetary orbits, the bending of light around massive objects, and the formation of black holes. But when we try to apply the principles of quantum mechanics to gravity on the smallest scales, for example, near singularities inside black holes, or at the very beginning of the universe, general relativity fails. It predicts impossible infinities, signaling the incompleteness of the theory. Thus, the existence of gravitons remains one of the most agonizing questions in modern physics. Scientists hypothesize that gravitons, if they exist, must be incredibly light, perhaps even massless, and they would interact very weakly with matter. That makes it virtually impossible to detect individual gravitons with any existing technology. Unlike photons, which are relatively easy to detect, because gravitons interact strongly with matter, detecting them would require detectors far more sensitive than anything we can currently build. Calculations show that a graviton detector would have to be as massive as Jupiter and located near an extremely dense and energetic source, such as a neutron star, to have any chance of success. Even so, it's unclear whether we'd be able to register a signal. A significant breakthrough in gravitational research occurred in 2015 when the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves discontinuities in spacetime caused by the collision of massive black holes. Gravitational waves are an indirect consequence of the general theory of relativity, reflecting the wave-like behavior of gravity. However, this discovery did not answer the question of whether gravitons, the quantum analogues of these waves, exist. About this, we'll talk more in detail a little later. Wave-particle dualism, a fundamental concept of quantum mechanics, suggests that gravitons should exist as particles of gravitational waves, just as photons are particles of light waves. However, although we've experimentally confirmed the wave-like behavior of gravity, the particle aspect remains elusive. In recent years, some experimentalists have begun to explore possible indirect evidence for the existence of gravitons. One of the most notable experiments this year was the discovery of chiral graviton modes in quantum materials that exhibit behavior similar to theoretical gravitons. In these condensed matter systems, researchers found excitations that mimic spin-2 particles, providing a potential experimental basis for studying graviton-like particles in the laboratory. Although these are not real gravitons, they provide insight into how gravitons might behave under certain quantum conditions. Despite these promising developments, a direct detection of gravitons remains beyond our current technological capabilities. However, physicists continue to explore various theoretical and experimental approaches to this problem. One of the most radical ideas about gravity is the possibility that it may not be a fundamental force at all, but rather an emergent phenomenon. This concept challenges the traditional view that gravity acts as an independent force, controlling the motion of planets, stars, and galaxies. Instead, theories such as entropic gravity and the holographic principle suggest that gravity may arise as a consequence of other physical processes, just as temperature is an emergent property resulting from the motion of entropy. A measure of disorder in a system plays a key role in this view. When objects move, they increase the entropy of the universe, and this increase in entropy manifests itself in what we perceive as gravitational attraction. According to this idea, gravity is not a fundamental interaction like electromagnetism, but rather a byproduct of thermodynamic principles. This scheme relates gravity to the statistical behavior of microscopic components, just as gas laws arise from the collective motion of individual gas molecules. Another compelling concept is the holographic principle, which comes from the field of string theory. It suggests that the entire three-dimensional universe, including the force of gravity, can be described by information encoded on a distant two-dimensional surface. In essence, our perception of gravity in spacetime could be an illusion, much like a hologram projects a three-dimensional image from a two-dimensional surface. In this scenario, gravity would be a manifestation of deeper quantum processes occurring at this lower dimensional boundary. In this context, gravity would arise as a result of the entanglement of quantum particles, subatomic entities that remain bound to each other even when separated by large distances. The more entangled the particles become, the more gravity manifests itself as a large-scale effect. This concept is mind-boggling, but relies on well-known principles of quantum mechanics. Entanglement essentially stitches together the fabric of spacetime, and the gravitational force we feel is a large-scale reflection of this fundamental quantum behavior. These emergent theories shift the focus from gravity as an independent force to gravity as a collective behavior arising from the underlying microstructure of spacetime itself. In some models, spacetime is not continuous, but consists of discrete units or pixels at the smallest scales. This pixelization of space can be so subtle that we cannot detect it directly, but its effects can propagate outward and cause the macroscopic phenomenon of gravity. Experiments aimed at detecting these emergent properties are in their infancy, but they offer tantalizing possibilities. Researchers have proposed using precision interferometer instruments designed to detect minute changes in space to look for fluctuations in quantum foam, the hypothesized fine structure of spacetime. By studying these fluctuations, scientists hope to gather evidence for the pixelation of space and, by extension, the emergent nature of gravity. If gravity is indeed emergent, it would fundamentally change our understanding of the universe. Instead of being a fundamental building block of reality, gravity would become a large-scale phenomenon arising from the collective behavior of quantum particles. However, scientists have some other views on this order of things. String theory and loop quantum gravity are two other attempts to reconcile general relativity with quantum mechanics, creating a framework for quantum gravity. Each theory offers a different approach to understanding how gravity works at the smallest scales. String theory fundamentally changes the way we think about matter and forces. Instead of viewing particles such as electrons, photons, or even hypothetical gravitons as point-like entities, string theory proposes that these particles are actually tiny vibrating strings. These strings are incredibly small, so small that, from our perspective, they appear to be dots. However, their different vibrational modes give rise to the variety of particles we observe. One of the most profound implications of string theory is that gravity is also a manifestation of string vibrations. According to this theory, a graviton, if it exists, will correspond to a particular mode of string vibrations. By assigning gravitation a place in the quantum sphere through these vibrations, string theory bridges the gap between quantum mechanics and general relativity. In addition, string theory introduces additional dimensions beyond the usual for 3 spatial and 1 temporal. It suggests the existence of up to 10 or even 11 dimensions, many of which are rolled up and invisible to us. These extra dimensions help explain why gravity is much weaker than other forces, since the influence of gravity can extend into these hidden dimensions, diluting its strength in the familiar 3-dimensional world. While string theory focuses on unifying all forces and particles through vibrations, loop quantum gravity LQG takes a different approach, attempting to quantize spacetime itself. According to this theory, space is not continuous, but is made up of discrete, finite loops of spacetime like pixels in a digital image. These loops form the fabric of space at the smallest scales, and gravity arises from their interaction. LQG is built on the idea that spacetime, when considered on extremely small scales, is not smooth but granular. These loops represent quantum states of the gravitational field, and the geometry of space arises from the network of these loops. The theory avoids the infinities arising in other approaches, for example, when trying to apply general relativity to black holes or the Big Bang, where the curvature of space becomes infinite. One of the key differences between string theory and loop quantum gravity is that LQG does not rely on extra dimensions. Instead, it modifies the geometry of spacetime itself by positing that spacetime is made up of discrete chunks that interact with each other to create the smooth continuum that we observe on large scales.